looks like we got a pretty good crowd on our hands. So again, thank you for taking some time out of your day to join us today. Just a couple quick little housekeeping notes on this platform. I will admit this is new to us too, but I believe you can see on the left-hand side of your screen, there's a question logo chat, which if you have a question during the presentation, feel free to type it in or chat it in, and we will either answer it as we go through the presentation or wait till the end and then try to address any questions you have. So fairly smaller crowd, so I think we might have some time at the end and answer any questions that you may have. All right, with that, again, thanks for joining us today. I'm Mike Lanners, the Director of Sales at DrySteam here. And today's live webinar will focus on the role humidity plays in mitigating airborne transmission of viruses. You know, just 3 months ago, the end of the pandemic appeared to be on the horizon. The vaccine results suggested a clear path forward. The return to normalcy would take some time, but after a year of uncertainty, the conclusion seemingly had come into focus. Well, that excitement has dissipated somewhat the last few weeks, as we all know, with the mutation-ridden variants that are popping up and that have been detected. The path forward is still hopeful, but perhaps longer and more complex than any of us really hoped for. Most experts are now saying that the virus is here to stay. Vaccines may have to be updated, perhaps regularly, and we will all have to prepare for the likelihood that over the long term, the novel coronavirus will become a persistent disease threat. We also know the virus is more contagious indoors. The new fresh look for post-COVID commercial buildings is placing a big premium on flexible, healthy, safe workspaces, which includes extra emphasis on improved indoor air quality. David Baird, our Senior Applications Engineer, is going to be the trainer and presenter today. David's going to hit on a few things. He'll present to you the role humidity plays in reducing the transmission of airborne pathogens. He will touch on the ASHRAE standards and guidelines coming out of the Epidemic Task Force. And he'll look at some practical solutions to achieve the desired 40 to 60% RH levels. Just want to also let you know that this presentation will last about an hour, and we will be offering a professional development certificate to PDH for joining us today. And that certificate will be automatically sent to you at the conclusion of the seminar. So with that, I'm going to turn it over to David. And again, please do type in your questions. I will monitor those, and we'll stop David if we have a question that's relevant at that moment. Otherwise, we'll wait till the end and answer your questions at that time.
Hey, Mike, can I mention something really quick?
Absolutely.
Hi, guys. It's Abby Rogers with DrySteam. I'm just hanging out here for a second. We've noticed that the PDH certificates are being sent to the junk mail folder in your email. So if you think you don't get it, please check the junk mail folder first, along with the presentation recording and the presentation itself. So if you don't see it right away in your mailbox, check the junk mail folder. Thank you.
All right. Thanks, Abby. All right, David, I'm going to turn it over to you.
Well, thank you. And thank you for joining this presentation. And so, as Mike said, we're going to really kind of look at, how COVID-19 really impacted our way of life a little bit, specifically in terms of airborne viruses and how we address that within the built environment. So as Mike said, we'll look at kind of the role humidification can play in terms of airborne pathogens and viruses, how humidification improves our human defenses as well. Look at some of the ASHRAE standards and guidelines that have come out over the last year from the Epidemic Task Force. We'll look at just humidification equipment and systems design. Where do you get started? Just general guidance. Then also look at some practical ways to kind of achieve this 40 to 60% in addition to maybe it's modifying existing equipment that is already on site. So humidity plays a major role in reducing the transmission and infectivity and improving defenses. You think of different things such as hand sanitizers and wearing masks and social distancing. All of these take active measurements. It requires active intervention in order to be able to address it. Humidification is one of those ways that can help from a passive standpoint. It's just always there if you maintain humidity within a space. And it can help, to make sure the space is safe and for those, as well as reduce that transmission of viruses such as SARS, COVID, and we'll look at how that's done kind of throughout this presentation using some of the different research that's come out as well. So relative humidity in buildings can have quite a bit depending upon climate. If we're in the north or in the south, depending upon that, depending upon the type of heating and cooling system, as an example. The amount of outdoor air that's brought in from ventilation purposes. Different spaces have different requirements depending upon where you are. Typically in winter, especially in northern climates, indoor relative humidity can drop to 20 to 30% or even lower than that, depending upon the construction and use of the space. And that 20 to 30% typically just isn't enough humidity in order to protect occupants against viruses and bacteria. Kind of that 40 to 60% range is where it seems that research is settling out, is kind of that ideal range. Not just for SARS and COVID, but also the seasonal flu, which is something that we've been dealing with for a number of years. So Professor Steve Welty, when H1N1 was around a number of years ago, provided some different input to the CDC as well as the ASHRAE in terms of some measures to kind of look at how to spread this, to stop the spread. And so a lot of them kind of look at a holistic approach. So a number of different things, looking at relative humidity, increasing ventilation, looking at UV, where exhaust is taken from, and as well as ventilation and filtration. So a lot of these different tactics together can be done to try and address the flu season and H1N1, which is still applicable today towards COVID, which is what we're dealing with in the pandemic. So there's been a lot of studies that have been conducted over the years. When H1N1 was around, in terms of the current pandemic and SARS and SARS-CoV-2, all of these are kind of pointing to a number of different things. And we'll look at just a couple of these. We already looked briefly at the Welty study as an example. And a number of these kind of are done in a clinical setting. One of them we'll look at a little bit more in detail is a clinic study conducted in an actual preschool, actually within the built environment. And so that one is quite interesting, kind of understanding what happens when it's actually applied outside of the laboratory setting. So many of us are familiar with the Stirling chart. And the Stirling chart shown on your right is one of those common ones that we reference in terms of trying to find what an ideal range of relative humidity in a space is. Looking at a combination of how it impacts viruses, bacteria, fungi, and other things. And you'll see that that usual range shown in yellow is in that 20 to 30% that we talked about, especially in winter conditions. The optimal range, kind of the best balance between a number of different factors, tends to be in that 40 to 60% range. And this study was back in 1986. It's still just as relevant today as it was then. And so just kind of looking at that ideal range, is the building actually in that ideal range? And most often not. So why do we talk about airborne viruses? Because SARS, COVID-19, H1N1, MERS, they all fall into this airborne virus concept. So really understanding particles within the air and how they're acted upon within the building is an important piece. How long the aerosols stay in the air? Do they fall if they're more moist? How far do they travel? How long do they stay there? All of these things are important things to understand. The concept of a 2-meter social distance, is that enough? Depends upon the activity, how long you're near someone, as an example. And what's the environment? What is the building doing in terms of air currents, as well as the environment, temperature and humidity, or even solar? So there's a lot of different factors to kind of come into play. So let's take a look at a sneeze. I know it's not something very interesting, but this is an example of a sneeze. And you'll notice that that sneeze, some of the particles go all the way up to 8 meters. So it gets to be a little bit more kind of than that 2-meter we talk about from a social distance standpoint. And so you'll notice some of the particles drop out really quick, and some of them spread a lot further. Well, the finer the particle, the further it'll spread, and the more it'll have an impact. And the built environment can't impact on those particles until they're ejected. And so the quickness in which it can do that and the particle size is an important piece. So in terms of particle size and droplets, okay, well, let's look at this particle size. So the larger a particle size, and this was done with a study with ASHRAE, just collected some data, you'll notice that kind of the larger the particle size, and we're talking about nanometers here, so really small size, that they'll last in the air for very little amount of time. The smaller the particle, the longer it will stay in. As an example, at a 0.5 micron, up to 41 hours versus 100 micron at 6 seconds. And the distance traveled is also quite a bit more. To kind of give some perspective, based on a Wuhan study, the COVID-19 particle was 0.25 nanometers. So all of these are an important piece. So, okay, particle size is important. Just like we saw some large particles from the sneeze dropped out quickly, the finer mist would spread further. Well, how does moisture play into it? Well, moisture is one of those things that kind of keeps that virus particle larger. Think of it as has coating of water around it, maintaining that the particle size doesn't shrink to get into smaller sizes so it can float longer, go further distances, and stay in the air longer. So in an environment that's dry, it will start to dry out, reducing the virus nuclei, allowing it to travel further and stay in solution longer. So those smaller particles is what we want to try and avoid. And this is where relative humidity, by keeping the space moist, can have a positive impact as a passive way to help address COVID or other airborne viruses. So another research study done in Finland looked at instead of cough, which is another common symptom associated with COVID. And you'll notice that, okay, I'm in one aisle. Depending upon the air currents, I may be infecting the person in the aisle right next door. And so how air is distributed and moving within the space and the particle size is key. Not just that distance that we're traveling from a sneeze, but also from a cough, because we're still working with particles within the airstream. And again, it's once they're ejected out into the space, can the built environment actually influence where they're going to go and what size they are. In a moist environment, they'll stay. They won't shrink in terms of size, which will allow them not to travel as far or stay in the air longer. Another important piece, and just kind of looking at the human body, is the smaller the particle, the further it can get within our body, in our lungs specifically. And then the further it gets in, the harder it is to get rid of, which increases our chances of getting infected and the severity of it. You'll see kind of right at the entrance, it's pretty large particles. And once you get into further into the lungs, smaller and smaller particles. So this particle size concept not just impacts how far it's going to travel, how long it stays in the air, but also how far it can make it into the human body. Well, the human body has ways to try and address and remove stuff. I mean, you think about all the pollen and stuff we get during the summer as an example. And so think of it kind of as a conveyor system. And this is where that moisture concept helps the human body. And so a mucous membrane with cilia helping to move stuff back out of our body. So besides the particles getting further in, the smaller they are, then longer distance it takes to try and get out, and impacts the way in which the body's mechanism of removing these particles comes into play. So moisture, besides impacting the particles, impacts the way our human body responds, as well as its ability to be able to heal itself. We're built of a lot of water, so being in a moist environment is healthy for us as well, to keep those mucous membranes to help stop those particles and capture them and then move them out of the body. Another study kind of looked at the particle size, and this looked at a number of different particle sizes. And you'll notice that once you reach kind of a 40% relative humidity, it didn't matter what the particle size, but that the infectivity was reduced significantly once you hit kind of that 40% relative humidity range. And so that higher relative humidity is a positive in terms of it impacts the ability to be infected, and it also is beneficial for our human bodies and our ability to be able to recover. And so I mentioned this study conducted with the Mayo Clinic in regards to it within the built environment at nursery. And this is one that was performed in conjunction with Dry Steam and the Mayo Clinic in a preschool in Rochester, Minnesota. And the goal of the study was to really kind of understand how much humidification could help. So some classrooms were humidified, some classrooms weren't over the same time period. And so looking at a couple of small electrode humidifiers added to try and maintain a relative humidity of 35%. And that would still put it close to that ideal range, versus some of the non-humidified rooms were about 20% relative humidity, which is pretty common in a cold environment in the winter. And so looking at kind of the results, they were looking for kind of flu-like illnesses. And you'll notice that in the control rooms, there was 70% of those were reported there versus 30% in the humidified. So flu-like illnesses were less from those within the space. Then you also get into air samples and then also on surfaces. And so having active humidification was beneficial in reducing basically the presence of those virus particles that couldn't retain as long. And then also, based on the kids that were actually within the space, their illnesses were also reduced. And just looking at that same data, so the chart on the left is looking at on surfaces versus in the air. You'll notice that in the control, where there was no active humidification, the amount of particles observed was significantly more than those in humidified, both on objects and in addition to the air samples. So let's look and see what ASHRAE has to say about this. So ASHRAE put together an epidemic task force to try and help provide guidance in terms of this pandemic and what to do to help guide the built environment through it. So statements kind of talk about, okay, keep using the HVAC equipment within the space. And that, additional guidance in terms of conditions and how to operate it, they provided along the way as well. But they talk about, ventilation and filtration are still important pieces. So don't turn them off. You still need to filter the air and provide ventilation. So two specific documents that are really good from the task force, as an example, provide guidance for opening schools and universities, and also kind of building readiness for when everybody gets to go back to the office, or if it's in stages. Both documents recommend HVAC systems. They talk about controls and operation, and they also reference maintaining a relative humidity between 40 and 60 as advised. And so specifically taken out of it, in terms of the one for schools and university, they include one of the strongest statements issued in regards to relative humidity, and talking about relative humidity levels between 40 to 60%. And you can look at this document more specifically, but it provides that guidance for them to kind of use in terms of comfort conditions. Another thing to kind of keep in mind with a lot of this is increased ventilation is beneficial. Well, if you think about a cold climate, then you're bringing more outdoor air that tends to be dry. It can't hold as much moisture, which will further dry out the building. And so bringing in more ventilation, yet trying to maintain a higher level of relative humidity will mean that the humidification loads will end up being more. There'll be more of a requirement to use humidification. So both of those factors together lead to that humidification systems become more important. Now, Dr. Stephanie Taylor, who's on the epidemic task force, had published an article in September of 2020 talking about this as well. And she talked about kind of working in cold climates and talked a little bit about adiabatic humidification. And you wouldn't think of that as typically being used in a cold climate. You don't have a lot of energy within the air, as an example. But she brought in several positive things and just kind of understanding how it can be done even in cold climates where in winter conditions, it's going to be not as much moisture outdoors, and it's going to be more important as we continue to bring in more ventilation. And we looked at the Stirling chart earlier, and in the article, they included an updated version of it. And you notice the top portion of it really includes the same things that we saw in terms of the Stirling chart, looking at viruses and bacteria and fungi and how relative humidity within the space impacts that. But they also brought in the bottom portion, kind of looking at what impacts does it have to the human body, whether it's productivity or quality of sleep, and just kind of general care and illnesses. So good to kind of bring in that holistic concept besides looking at just what's happening within the space, but how the occupants are being affected by relative humidity as well. In all cases, you look at that ideal range, everything's pointing to that 40 to 60% relative humidity seems to be where humans suffer less illness due to infections, and it's good for us, and we function properly as well as reducing those viruses, bacteria, fungi. Everything seems to be pointing directly in that space. But the reason why we don't go too high, though, is just concern of how much moisture a building can take. And so bringing more outdoor air means a higher humidification load and then a higher space dew point as well. And so if it's cold outside, we are trying to avoid condensation, generally a bad idea. And so something we want to kind of watch for is how much can the building actually take? We don't want to put too much that you start condensing on windows or starting to get into absorbed in terms of the walls, and you potentially cause problems. And so you think about summer conditions, there's a significant emphasis on reducing the amount of humidity within the building. And so it's a balance point that needs to be considered. One of those means to try and help with that is having some sensors on the outside of the building to try and make sure that you're trying to put as much moisture as the building can handle while setting back. So think of it as a setback. And so concept is a window transmitter that senses what the temperature is on the outside of the building, such as on a window, to set back the relative humidity set point so you don't condense on those surfaces, as an example. Nice way to kind of help from the controls. You're trying to make the space as safe and as possible by raising that relative humidity while not causing building issues. And so just kind of thinking about it, so overall, all the research seems to be pointing to this 40 to 60% relative humidity. It's a safe, easy, efficient way to help reduce that spread of the virus. And it's one of those passive. It doesn't require active intervention of social distancing, wearing a mask, wiping down surfaces. It's something that just is running all the time. And the addition helps protect the occupants as well. It helps the human bodies in addition to helping to reduce those virus transmissions, as an example. And so they can be installed independently, whether it's putting a unit on a wall within a large space, as an example, that you see in that top picture, or maybe even integrated within a building system, tied into an existing air handler that's serving the space. Both of them have slightly different ways in which you need to kind of apply them. And it partially depends on what the space is, what amount of relative humidity you're trying to add, and where you can disperse it. So let's take a look at an example. So let's just take a hospital as an example in Toronto. And so bringing in cold outdoor air, about 30% for ventilation purposes, trying to maintain typical comfort conditions within the space. So we understand, okay, we're bringing in cold outdoor air. We're going to need to humidify that to try and maintain the space conditions. So where do we get started? And generally what I like to think of first is, what energy sources do you have available? So do you have a boiler on site? Well, okay, if I already have a boiler on site, maybe I can tap into it, assuming I have enough capacity, because it doesn't require anything else to generate the steam. But if not, then is natural gas available? Natural gas tends to have a lower operating cost than using electric heaters as an example. But maybe there's space constraints or natural gas isn't available and need to look at electric humidifier. So just kind of looking at what energy sources and what operating costs. It's a balance between installation cost versus operating cost. Or maybe it's even looking at a water-based system. So looking at a wetted media system or high pressure atomization. And in that case, you get the benefit potentially of humidification and cooling at the same time, just based on that process. So either a steam-based system, where we're adding all the energy to the water initially by making it steam, or we're taking energy out of the air by using a water-based system. So looking at them a little further, we talk about isothermal. So these are these steam-based systems. And you've got pressurized steam, so coming directly from a boiler. We're talking about PSI, a number of different products there. Or if we have to boil water ourselves, think of it as a tea kettle. So a couple inches of water column is what we're working with, whether it's a natural gas humidifier, electric humidifier, a couple of different ways to create steam. And isothermal systems tend to be more common. Otherwise, you have the adiabatic or water-based systems as well, which is the pressurized water or wetted media, both systems. So those provide both cooling and humidification at the same time. So I mentioned that generally it's cheaper to operate a natural gas type unit. And so if that same space, going back to the hospital, so the humidification load happens to be about 34 kilograms an hour for that example, running about 5,000 hours. Looking at the energy rate, you'll notice that electricity costs about $9,000 more to operate per year. May have a lower installation cost, but the operating cost may quickly, in a couple of years, outweigh the initial cost of putting in, that gas humidifier instead. So just taking a look at not just the upfront cost, but the operating cost is an important consideration. So now that we've, determined that, okay, we want to use a humidifier, now it's a matter of how do we disperse it? And dispersing this steam is an important piece as well. Where do we have space available? And so if we're putting it into an air handler, how much space? Are there fans and filters downstream that I need to worry about? And this is where this non-wetting distance comes into play. And the higher the relative humidity I'm trying to maintain, or the amount of tubes that go into play. So if you look at that short non-wetted distance, there's more contact points with the airstream. There's more tubes in the airstream, allowing it to be absorbed faster. If I reduce the number of tubes, the non-wetted distance gets to be increased. If I only do a single tube, you'll notice that you move to kind of this long concept. And so in a duct, you may have enough space to be able to do it, but in an air handler, there tends to be a lot of stuff trying to be crammed within that air handler. So it's an important piece to kind of understand not just how I'm going to generate this steam, but how am I going to disperse it, and where do I have space to be able to do that, and looking at that performance. But in general, think of more contact points. The shorter the non-wetting distance, the faster it'll be absorbed, and the more opportunities you'd have to be able to install it within the space. one of the disadvantages potentially with having a shorter non-wetting distance is you have more mass within the airstream. You think about, okay, I'm putting 212 degrees steam into the airstream, and maybe the airstream I'm trying to maintain is 55 to 70 degrees. I don't want to heat it up too much. One way to offset that is to look at insulating those dispersion tubes. And by insulating, I can reduce the amount of heat into the airstream. At the same time, I also reduce the amount of steam that collapses into condensate, which is energy wasted. And so using insulation can reduce that amount by up to 66%, depends on the conditions. Just kind of keep in mind that not all types of insulation are the same. So PVDF tends to be the best performer, as you see on the chart on the side, versus non-insulating tubes. So it can have a pretty big impact if I can reduce the amount of basically heat loss to the airstream and steam loss to condensate. I essentially can boost the capacity of a humidifier as well. So let's go back to that hospital example. So same thing, this insulation versus non-insulated, how much does it actually come down to in terms of dollars and cents? Well, the amount of steam that's going into the airstream is exactly the same. So the heat gain from the steam, that 212 degree steam, ends up being the same at 0.3 degrees Celsius. Using the same on center, so the same amount of mass within the airstream, if I don't insulate it, I end up adding twice as much heat into the airstream, instead of from 0.2 degrees Celsius to 0.4 degrees Celsius. And the losses then also are more than double. Instead of 2 kilograms an hour, up to about 4. So over the course of that whole operation, we talked about roughly 5,000 hours. That ends up being about 11,000 liters of water per year of wasted energy, in addition to water down the drain. So insulation can have a big impact on just the operation and in terms of performance and efficiency. So where do you get started? Well, first off, kind of understand the space that you're working with. What relative humidity can be maintained within the space? Is it in that 20 to 30% we talked about from typical winter conditions? Or is there actually humidification on site? What is it able to maintain? Targeting, we talked about this 40 to 60% is ideal. So if we use a target of 45% as an example, how often are you able to maintain it? Okay, if there is a humidifier on site, is it working properly? Can I increase the set point on that humidifier to try and bring it closer towards that ideal 40 to 60% range, just by raising the set point? Or maybe we need to, add active humidification, just like what was done in that preschool, changing it from about 20% to 35%. And so looking at with a local sales agent to try and identify what the options are. So what about working with existing equipment? We typically always design equipment for kind of a worst case scenario. So as an example, if there's an active humidifier and we're set at about 20%, well, that means on a non-design day, I can probably cover off what I need for a portion of the time. If it was initially designed for 30%, well, then I'm going to be able to cover off more of those times. So depending upon what the initial set point is, by raising that set point, I can probably cover a portion of time. And that kind of depends on what it was initially designed for. So just think of those non-design days, you have additional capacity to potentially use. And so looking at kind of the way in which it is within the space to understand what could I get by with. And maybe on that coldest design day, I don't have enough capacity, but on a lot of the others, in between days, I might have enough capacity. And then thinking about, okay, we talked about once you drop it into an airstream, knowing what that non-wetting distance is. Well, what if we were to just add another humidifier to that And that might be able to, besides raising the set point, a little bit of additional capacity would allow it to reach into that ideal 40 to 60% space. But then you may run into a limitation of, I can't put enough potentially within the air handler, as an example, because the non-wetting distance would be too much. Well, it may be looking at adding another humidifier with a dispersion into a supply duct somewhere downstream after it leaves the air handler. As an example, using a trim concept. Or maybe even adding a whole nother branch of ductwork that would allow to have that distance to be absorbed. So just looking creatively at increasing capacity and then also understanding where can I add that steam while not impacting other things within the airstream, whether it's filters or fans, is an important consideration. In terms of adding another humidifier, well, it'd be nice if they work together as a system versus independently, and being able to do that with multi-tanks, so that way on a light day, only one of the humidifiers is running, or if both of them are needed based on a design day, then they're operating together. And so a multi-tank arrangement allows to be able to pair two systems up together to meet that load and balance the wear and tear on each one of them by having them work together to achieve basically a bigger system, yet using redundant type devices. And we talked about kind of this non-wetting distance. So here's a practical example. So let's say that the dispersion system was designed with 21 degrees Celsius in the space, 17,000 cubic meters per hour at 30%. If the set point was 20% relative humidity, it's 152 millimeters. Raise it to 30% relative humidity. Now you've just about doubled it to 254 millimeters. You take it up to 40 degrees Celsius. Again, you're just about doubled it to about 457. So adding more moisture by raising that set point, knowing that non-wetting distance and what is downstream that may be impacted, if there's takeoffs or a bend, need to kind of keep that in consideration to make sure that the steam can get absorbed, because now we're adding more to the airstream. Then what about looking at the economizer set point? Maybe that's another way to look at it. So as an example, if the economizer set point is 55 degrees Fahrenheit, that's where you would bring in 100% outdoor air. So you've got this humidification load. Well, what if the economizer set point was raised to potentially 60 degrees Fahrenheit? Well, in that case, then you would be bringing in less outdoor air when it's really cold out, meaning that your humidification load would be less and allow you to be able to get by with that same size humidifier without changing things. As an example, you'll notice at 40 degrees Fahrenheit, your load would drop from 82 to 55 pounds an hour. Pretty sizable reduction just by looking at that economizer set point. Just looking creatively at it, it may impact your ventilation, but you'd still be maintaining a minimum ventilation set point in addition to the economizer. But just another creative way of looking at how can you get additional capacity. Going back, we talked about insulated tubes. Well, what if by changing the dispersion assembly to add insulation, I again can reduce the amount of heat gain into the airstream, which is beneficial, and reduce the amount of condensate loss, allowing me to have a little bit more that goes into the airstream. So the amount that's generated and dispersed, more of it's making it into the airstream versus going down the drain. So that's another creative way to kind of look at it. Then thinking about from the generator side of things, let's just say we're working with an electric humidifier. We talked about this, what we can do with the dispersion assembly, but what about looking at the amount of power required? And so the more we're trying to create from humidification, the more energy is going to get consumed. And so taking an example of an electric humidifier from 14 kilograms an hour going up to 29 kilograms an hour, the amount of energy is going to double as well. is there enough electrical service in order to be able to handle that? That's definitely a consideration. Or if it's natural gas, is there enough volume to be able to handle that? Is the pipe size big enough? So different things to think about is as we try and add more humidity to the space, there's going to be implications in terms of energy usage as well as the dispersion. Taking the existing dispersion and trying to put more through it, can that dispersion assembly handle it? Just kind of going back, I was thinking as well as, kind of changing the dispersion assembly around besides adding insulation. What if we were to retrofit it to handle a higher capacity? That's another option. In this case, you happen to add another generator. Well, that dispersion assembly, maybe it can be retrofitted to handle that additional capacity. So without looking at the insulation, but maybe insulation and changing out basically the orifices that are used within it to handle higher capacity. Again, just looking at creatively with minimizing the amount of impact to the building. And so, okay, let's say you're working with pressurized steam. Well, what if the pressure set point were raised a little bit? Whether this is a steam-to-steam heat exchanger, and this is just, a steam-to-steam heat exchanger, increasing the steam pressure from 5 psi to 10 psi, I can get more capacity out of it, yet it's the exact same device. The same would apply if it's a pressurized steam dispersion assembly. By increasing the psi by a few psi, I can get a little bit more capacity out of it, while keeping in mind, the implications in terms of the dispersion, what that non-wetting distance is, that can handle it. But just looking creatively at it, use same CV valve, or maybe it's even looking at, could I change out the steam valve associated with that dispersion panel to give additional capacity while not changing the steam pressure? Again, making sure that dispersion assembly can handle that is an important consideration and something that your local representative can help you address and look at. So, there's a lot of different things to think about in terms of retrofitting and trying to raise that relative humidity. But in general, in order to install a humidifier, it's generally looking at a couple of things. You have to have some form of energy, you have to have water, and you have to have a drain. That's typically all that's required. Maybe it's working in a classroom and there's a sink already in there. Well, then you'd have water, you'd have potentially drain, and all you need to do is address energy at that point, maybe an electrical conduit to be able to handle that. And so Cypress Sales can help kind of look at that, what's the appropriate size and type of equipment. Then also working with us as a manufacturer to kind of look at what those options are and to be able to get equipment as quickly as possible, potentially. Sometimes just getting things as quickly as possible in order to meet a need. Depends on what's going on. As an example, working with all these different manufacturers for creating vaccines, there's more of a need for humidification and storing, so sometimes jobs get rushed. Just kind of the way it is. And just sometimes looking at creative solutions. We talked about a couple of different ones, whether it's raising the set point, changing the economizer temperature, looking at insulation, retrofitting things. There's a lot of different creative solutions that are available to look at in order to increase that humidification. And so I just want to kind of end with a quote by Justice Archie Chamble. Just the point is not who is right and who is wrong about airborne transmission, nor is how far large droplets travel. The point is not science, but safety. Scientific knowledge changes constantly. Yesterday's scientific dogma is today's discarded fable. When it comes to worker safety in hospitals, we should not be driven by the scientific dogma of yesterday, or even the scientific dogma of today. We should be driven by the precautionary principle that reasonable steps to reduce risk should not await scientific certainty. And so this was published when H1N1 was going around. And so, it applies just as much now as it did back then. Humidification is common sense science that when it comes to helping to protect building occupants, as we talked about, it's better for our bodies. We are better in a moist environment, in addition to how it impacts different things within the built environment, virus transmission as an example. And so we can make this change immediately and easily. And so there's a number of additional resources that DrySteam has available. White paper talking about these same type of things, looking at how humidity impacts a virus transmission. A lot of different research studies are available as well, and case studies with what have people done in order to apply humidification to different buildings. So I'd encourage you to check out some of those resources. So I'll open up for any questions that you might have.
Thanks, David. We do have one question that was typed in here that we're being asked about ultrasonic humidification and in terms of energy use and dispersion and efficiency. I'll just say real quickly that currently DrySteam does not offer an ultrasonic technology humidification, although we are looking at that very strongly. But maybe, David, I don't know, do you know, can you speak to the energy use of ultrasonic versus other types?
Yeah, and just we talked a little bit about kind of those steam versus water-based systems, and there's a lot more, it seems industry is shifting a little bit more towards those water-based systems, whether it's an ultrasonic or a high pressure or a weighted media type system, partially because of the very low energy usage. Now, because all you have to do is move the water as an example. The thing to keep in mind there specifically is you still have to have the energy in the air in order to be able to absorb that water. And so that's a key consideration. If you're working in a cold climate and you don't have excess energy within the building, let's just take as an example exhaust from the building that you could use to help temper that air, then, you know, looking at it from an entire building standpoint, you'd have low energy usage of the device itself, but then you'd have energy usage that you may have to do in terms of preheating. And so looking at both of those is an important consideration. It depends on the application. But ultrasonic does tend to be rather efficient, just a piezo disc oscillating, but you have to have, basically the air has to be able to shed some energy in order to be able to absorb the moisture as well.
Excellent. There's no other questions at the moment, but we'll give it a minute or two to see if anybody wants to type in one real quick. Otherwise, yeah, we are done presenting. We'll just give it a little bit of time here and see if there's any other questions that anybody wants to throw in there. Just a real quick plug for our local rep up there at Cypress Sales. I'm assuming you all know Dan Kaminsky, our rep, but that is who our rep is, Cypress Sales.
Yeah, and I'd encourage, you know, we talked about a number of different creative ways to look at things. I think kind of keeping in mind that with this whole pandemic, there's been a lot more just kind of interest in terms of getting into how much the human body impacts with water and relative humidity, and more of an emphasis of it. It's one of those things that often tend to be kind of value engineered out. And I think there's just a lot more awareness through this pandemic, as seen by ASHRAE as well. And it's probably going to be a number of years before you see codes that actually increase some of those measures, as an example. But the science all seems to be there to help support it. And so I think that's where just being proactive about it, as try and, you know, reopen buildings and get kids back in school, and just some of those preventative measures. And, you know, that passive concept that seems very appealing. I think a lot of those preventative measures that we're doing now will continue, but having other passive measures is not going to hurt anything at all.
Right. Yeah, we are certainly starting to see work coming our way from this whole pandemic, I guess, the silver lining, if you will. But I think that the indoor air quality topic is certainly being looked at very seriously, and however we can help you folks, we're here to answer your questions about humidification, and look forward to being able to help you out with your project in the future. So with that, we do not have any further questions, David, so I think we'll go ahead and wrap this up. Dan Kaminsky, our rep, is just saying thanks to us via chat. And again, you will be getting a PDH email to you. Please do check your spam. It may go to your junk mail, but they should be coming out. If you are looking for that and it did not show up, please contact either myself, Mike Landers here at DrySteam, or Dan Kaminsky, and we'll make sure we get that to you. With that, we'll sign off and wish you a good day. Thanks for your time.
Thank you for your time.
Bye-bye.